Okay, let's jump right in. So, first of all, sorry for my appearance. I just got off work. Harry's eyeing me from across the room. I spent all day rolling around in some dirt, so I'm a little dirty right now. I'm gonna go shower after this, but I got home and I sort of had a bunch of emails to respond to regarding this homework and this lab. Um, which I was totally anticipating. I know that this is one of the trickier concepts for many of your to wrap your brains around. It certainly took me a second to understand sort of the majesty and the vastness that is geologic time. Um, and so I thought I had a video already made of this, but I didn't. So I'm going to make one to help you walk through the lab and the homework for Module 5 Biosphere. So this is for the lab. If you have not started the lab yet, or if you have started the lab and you're lost, let's walk through it real quick. This is the map of geologic time. This is the pre-lab text that you should absolutely read through because a lot of this is going to be really important coming up here shortly. Uh, Especially these three laws here, the law of original horizontality, the law of superposition, and the law of cross-cutting relationships. And each one of these three blocks sort of represents what these laws mean. So the law of original horizontality, I know I talked about that in the lecture, but let's recap real quick. Essentially states that everything, sedimentary rock is deposited as a horizontal layer, right? It's not going to be deposited as waves. It's not deposited as a slanted slope. It's always deposited horizontally. And that has to do with gravity, right? It's going to be deposited nicely in a horizontal way, like this first block here. Only then, after we have had many layers deposited, we might have a massive force like tectonic movement or plate movement that adjust or change the rock to look more like this. Think about how that could happen in a tectonic setting. What sort of tectonic boundary do you think is going to cause horizontal strata to get smooshed like this? Sort of gave you some big hints here. But only after is it deposited horizontally can that occur. And then finally, the law of cross-cutting relationships. When we have an igneous dike, or a magmatic system that sort of jets through some of this horizontal material, that's going to be younger than in any of this material here because this was already deposited and then all of a sudden you have something cutting through it. This is how we date sedimentary rocks. We cannot carbon date sedimentary rocks. And I'm not going to tell you why. I don't remember if I tell you in the lecture or not, to be honest. Because I think I have a question coming up regarding that. Uh, we can't date sedimentary rocks. We can only really date igneous rocks. Igneous rocks crystallize out of magma, and as soon as they cool, that crystal is set, and we actually don't necessarily radiocarbon date. We do a bunch of other type of dating, but we can accurately measure the age of those rocks using science. But we can't do that in the same way with sedimentary rocks. We have to use other methods. And one of these methods is understanding stratigraphy and how they align with each other. And the Grand Canyon is such a beautiful example of this, right? We have these beautiful, colorful layers of strata in the Grand Canyon. And we know that the oldest rock in the Grand Canyon, which I think is 2.6 billion years old, is at the very bottom of the canyon because that's where the oldest material is going to deposit first, right? It's depositing at the bottom. And then over time, you're going to have other layers that deposit on top and on top and on top. So we start with oldest material at the bottom and we work our way up to younger and younger and younger. So for our first activity here, relative dating, and I do want to apologize, I had to split it into two because Canvas is stupid. Um, it's the same concept. You're going to start at the bottom and you're going to work your way up. And I did want you to think about this process a little bit as you worked your way through it, but you'll know we have two different sections essentially of this block, right? We have this weird section at the bottom that's all squiggly. You're like, that's weird. How did that happen? And then we have this other block on top, or this other half of the block that's very horizontal, very straight. You're like, oh, that's weird. How did that happen? But I also want to point out this line here, which my first follow-up question asks about, H. What does H represent? This line is essentially separating these two entities. And I write very clearly what that could be in this pre-lab text. So think about, at one point, think about how this used to have to be horizontal, right? That's the only way it could be deposited. This part of the block had to be horizontal. And over time, at some point, tectonic processes, smooshed this into these beautiful folds and waves. And then something happened at the top of this area, this unit, um, before another unit was deposited, but perfectly horizontally. So that's what I want you to think about what H is. And this is where shit gets weird, right? This is where you're like, what? I can't wrap my brain around it. Read the pretext. Think about what some of those words mean. And think about how these two units could be so different and what is happening at H that is causing these two units to be so different. Same with E. Think about how E here arrived here. And K down here is also part of the H. Think of what K is cutting through here. And if that makes it older or younger than some of these units. Okay, so start with the oldest. I've already given you the first, well, I guess I did it in the lecture. But the oldest unit is B. And I don't feel bad giving you that because it's at the very bottom. And it's a good place to start. So start with B and then think about what's going to come after that. Okay? Here's the thing. If you mess up one of these, but you get all the other ones correct, I'm going to fudge some points on there for you. If you get, because if you get one of these wrong, it's going to be like, no, you're super wrong. But if you're like, well, I think, for instance, Q fits into this one, and then you're like, these next four are correct in order, I'll fudge those points for you. So don't stress too much. If you get some of those wrong, I'll go through and fudge that for you. Okay, so these are all follow-up questions. Read the pre-lab. And then we're going to jump to fossils. So the whole point of the biosphere module was to understand that fossils and living organisms are the best way that geoscientists have had in measuring geologic time in the stratigraphy that we can't date just by taking rock samples from, right? We have to find other methods and other ways to date these rocks. And so the best way to do that is finding these fossils in the geologic record. So here's a Word document. I don't think that has all of the information that is in Canvas, the Canvas quiz as well. It's just, oopsies, that it goes all the way back to the top. So it has all of these, right? If you don't want to be scrolling back and forth and back and forth. You're going to get to this part here where these are the instructions. Maybe I should make a little headline that says instructions. Where you're going to examine 5 of these 8 fossils. So you can choose any one that you want. I don't even care. You can pick them out of order too. You can go 7, 4, 2, 5. I don't care. Live your life. We're going to pick fossil 1. I actually already did, but I'm going to do it again. And it's going to bring up this beautiful 3D model for you, right? Oh, it's stunning. It's our gastropod. Back to, nope, we're in lab. Oof, sorry. And you're gonna do this 5 times. You're gonna pick 5 of these, and you're gonna give me the fossil number. So I would say, okay, I picked fossil 1. You're gonna give me the phylum. So here's where we're gonna go kind of back and forth. This does not have a phylum. It just has a really cool name, and it has a really cool shape, which we'll come back to here in a second. This one is left. We're gonna go back up to. No, I went too far. I went too far. I know it's in here. Here it is. You're going to find gastropod. Oh, gastropods. Here's what they look like. Here's a description. The phylum is Mollusca. Mollusca? Mollusca. I don't know how to say it. You're going to put that into number 2. My phylum is Mollusca. Your sample description, this is where you're going to go back and you're going to be like, oh, it looks kind of conical. You don't have to get crazy here. I'm not asking for a paragraph. It looks conical. There's like 3 different, 4 or 5 units. It looks like a snail shell. If you want to be like, I'm going to bring in my modern stuff into this, you can get crazy. Say it looks like a shell or a snail shell. I love that. Your age range. So this is where it does get important because this is the whole point of this. Your name of geologic periods is what I want here, not numerical dates. So what I mean by that is you're going to have to go back up here. We go to the Word doc, find your mollusca. I went too far. And here we see our gastropods. And our gastropods existed from the Cambrian to the present. And every single one of these has these named dates. And you're like, I don't know what that means. Oh, I'm so glad you asked. So the Cambrian period is this green period here in the geologic time history. And present, obviously, is over here. So is right now. I shouldn't say obviously in regards to this map. You might not be super familiar with this map. So the present is here, and the Cambrian is all the way down here. And just so you know, I'm not asking for numerical dates, but the Cambrian starts 540 million years ago. It's a long ass time for these critters to be alive. Oh, the kitties just got fed. Yay. Okay, so that's what I'm asking for there. Oh, and then the last one was, oh, I think just the name, which again, yeah, was gastropod. That's all it is, gastropod. Yay, easy peasy McPeasy pants. I had a student text me today or email me today and say, is it supposed to be that easy? And I'm like, yes, I don't want you to overthink this part necessarily. I want you to understand. I want you to start getting familiar with some of these geologic names. Cambrian, Permian, Ordovician. You're going to start seeing these names, and I want you to become familiar with them because that's the whole point of this is understanding geologic time and how how the biosphere fits into geologic time. So you're going to do that 5 times, 5 different fossils. And then we're going to jump to mass extinctions, which we have 5 mass extinctions in Earth's history. And there's this really great book, I just got it out actually, called The Sixth Extinction, If You Want to Feel Sad. It's actually an incredible book, and it's very well written. It won the Pulitzer. And it's essentially how humans are currently living in the sixth extinction because, we're killing ourselves through lots of really fun ways. So these are the 5 mass extinctions. We had the Ordovician, Devonian, Permian, Triassic, and Cretaceous. And you're going to go back to the fossils that you chose. So remember, you could pick 5 of 8 fossils. And did any of those organisms that you chose, did any of them go extinct? And you'll see these words. So anything that has not lived until present has gone extinct. Some of them might surprise you. So then these are all questions based on the mass extinction. Oh, yay. Nothing crazy. Yes, a lot of it is open-ended. Because I want you to think about, again, this is a very conceptual module. And it can be hard to wrap your brain around. I'm not trying to trick anybody. I'm not trying to get you to get crazy. Which extinction was largest in Earth's history? Go back to this map and take a look at some of the numbers here and why that is. I guess it doesn't tell you why, but how that happened. It does tell you how. Extinction, when did dinosaurs? That should be pretty easy to find. Index fossil. Oh. I do talk about index fossils in the lecture, so I'm not going to explain that here, but do your best to think about which of your fossils, your 5 fossils, would be best used as an index fossil. And which ones can be found today. This one is going to be open-ended. Don't overthink it, but I think it's a really good thought. I'm sorry, my brain is completely fried. I've been working for 8 hours. Process. It's just something really interesting to think about. What do you think mass extinctions say about the durability of the Earth? We've already had 5 of them. Think about where we are now. Think about what ecosystems and what the biosphere looks like now. It's incredible, honestly. But I want to hear what you say about the durability of the Earth, right? So it's a little bit more subjective. So that's our lab. Hopefully it's relatively straightforward. I just added something to the homework. So if you started the homework and you're now watching this, I do apologize. I did do it on purpose, and then I realized when I was getting some emails, I was like, okay, I'll put it up here. So here is geologic time. We're gonna do an activity with some math. And in my brain, I guess I was like, everybody has access to calendars. They can work through this. But I was trying to keep this out of here to make this a little bit less bulky. But I think I need it up here. So here's the calendar that will be really helpful to use when you're doing this activity. So I give you an example. Okay, hold on. I guess I'm getting ahead of myself here as I'm overthinking everything in my brain too. So the point of this is you are condensing geologic time, which is 4.6 billion years, of time. You're condensing that into a single calendar year. And the reason we're doing this is because I just think it's a lot easier for you to conceptualize something as vast and massive that geologic time is, and really quantify how much time humans have actually spent on Earth. And it's unbelievable. It's such a mind-blowing concept to me. Um, and I work with one of my best friends, is an archaeologist, and she's like, "Oh man, I found this artifact that's 6,000 years old." And I'm like, "Okay, but I found a rock that was 3 million years old, so it's not quite the same." But it's mind-blowing to me that I work on such m massive time scales compared to a human time scale. And that's what I want you guys to get out of this, right? So the good news is once you do this math equation once, hopefully it'll be um, just a plug and chug from there. I did that on purpose. So I give you this example. The dinosaurs would extinct approximately 66 million years ago. I'm just going to tell you now, this is one of the options down here, so you can use it for one of your Mesozoic events. You're welcome. Okay, so we're essentially setting up a ratio, two ratios between calendar years and uh, 66 million years to 4.6 billion years. So this is when dinosaurs died. This is the age of the Earth. This is the length, oopsies, sorry. This is the length of the calendar year. So what we're doing is we're solving for the date in the calendar year based on the date that we're given. So when we do this equation, the denominators for both of these ratios will stay the same. You're not changing them. You're going to keep 365. You're going to keep 4.6 billion. You're going to change this number based on these here. And, oof, I also just realized, I do apologize. I did not explain MA or GA. So I'll get to that here in a second. Or KA. My apologies. I'll write them down at the bottom, actually. Hold on, I'll do that now, right now. Okay. So just real quick, I put in the bottom here, KA just means 1,000 years. So end of last ice age, 20 KA, that's 20,000 years ago. MA is millions of years. So largest Yellowstone eruption was 2 million years ago. And then GA is billions of years. So you're going to see this oldest rocks on Earth are 4 billion years old. They're actually like 4.3 now. We just got some research that are saying that they're about 4.3 billion years old. It's so cool. But we'll just use that number for here. That's fine. Okay, so back to our ratios. All you're doing is cross multiplying 365 times 66 million years. Okay, once you have that number, I like to use my big graphing calculator for this. If you do use your phone for this math, you might have to turn it on its side. I've done that. Woo. Ugh, I hate the new calculator thing. Okay, so you're going to do 365 times 66 million years, boop, 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 equals, and then I divide it by 4,600,000,000. Make sure you have the right amount of zeros. Did I overdo it? Nope. Okay. So you're going to cross multiply and isolate x. Here's the math down here if you want to set it up this way. You're going to divide this by 4.6 billion years. And you're going to get approximately 5.237 days. Okay. So 66 million years is 5.237 days from the end of the 1 year calendar. And then the 0.237 days will go into hours here in a second. So because we're looking at the past, when we're looking at this here, we're saying the dinosaurs died 66 million years ago from today, right? So this X that we got 5.237 is 5.237 days ago. And if present is the end of the calendar year, let me zoom in here. We're going to go back 5 days from present. So we're going to go 1, 2, 3, 4, 5. The dinos died on December 26th in our calendar year. Just want to make sure I'm not crazy. Okay. Yeah, December 26th in the 1-year calendar. When you do 0.237, so hours, when we're doing the hours here, the 0.237 days, the decimal at the end of the 5, when we're converting that to hours, you're going to think about how many hours are in a day. There's 24 hours in a day. You're going to go 24 times 0.237. So I multiplied 24 hours by 0.237 to get how many hours? And I got 5.6 hours. So when I go down to question, I guess it won't be Precambrian, it will be Mesozoic. I would say I chose the dinosaur extinction. They died December 26th, and they died 5 hours prior to that. So they died at oh God, time 12. So they died at 7 o'clock around. That's fine. Around 7 p.m. on December 26th, the dinos died. Here's the thing. I know that math and counting can be a little tricky, so I give about a 1 to 2 day leniency on these periods. I give a few hours leniency, but if you're telling me that the dinos died in July, I'm going to be like, dude, I don't know what you did with your math there, but that is very wrong. But if you're telling me, hey, the dinosaurs, I'm getting the 27th, I'm like, that's close enough. You just counted 1, 2, 3, 4, 5 instead of back 1, 2, 3. Totally fine. I'm not going to be mad about that. But if, again, don't pick a July date. Make sure you're in the 1 to 2 day range of reasonable times. So you're going to do that for each 2 of each of these events. Okay. So that is the math for this. Again, you're just changing this number here. So if I wanted to go in and say, oh, let's do Permian extinction, 250 million years. MA is millions of years. You're going to go up. You're going to do 250 here, but keep these the same. Multiply 365 by 250 million, divide by 4.6 billion, and you're going to get another number. So this here that I'm stating is, again, I think this is going to help a little bit better. Here my brain was like, don't understand calendars, but that is on me. That's 100% on me. Having a visual is really, really nice. So if you get to, what did I say? If you get 145 days ago, if that is X, right? Because we did whatever event, the Permian extinction 250 million years ago, right? And you get, I don't know if this is how long it is. This is just an example. If you get 145 days ago, you can be like, well, that's a lot to count backwards for. I'm going to subtract 365 minus 145 to get 220 days. And you can count that forward now. Oh, and then I have this here. In this case, it's August, days 213 to 243. And you can go 13, 14, 15, 16, 17, 18, 19, 20. Oh, it's August 10. Look at me go. So that might be easier for you if you want to count forward, but you'd have to subtract from 365 to get to that number. If you're still struggling with this, shoot me an email. Happy to chat. You're going to do this 6 times, I think. You're going to do 6 different events. And then you're going to answer questions about the geologic timescale. It's, and how, and then the last one is which period of geologic time would you want to visit? I don't know. The one with the dinosaurs? Actually, it would be fun to do the Carboniferous when all the plants were just everywhere. So that is the homework. It's the extent of the homework. I apologize for not having the calendar before. I realize now that that was probably a pertinent part of the assignment. And so I do deeply apologize. You have it now. If you're struggling with this, reach out, shoot me an email. I really hope that this gives you a really good sense of geologic time. If you've ever watched the show Cosmos with Neil deGrasse Tyson, he does this too. He condenses everything into a calendar year, which is sort of where I got this idea. And I did steal a little bit of this from Western's geology program as well. So, reach out with any questions, concerns. Oh, here, I'll stop sharing. You can see all the dirt on my face. And I know this is a tricky module. I do. I understand. I respect that. And I will not cut it out of my curriculum because I think it's a really important topic to know. So, have fun with it. That's all.